Okay, so good morning and welcome to our second webinar that we're hosting in January. For those of you that joined us last week, we heard from Asher Fullerton and Alice Larkin and Chris Jones from the University of Manchester, who were talking about the potential role of ammonia as an aviation fuel. And today we're talking about the non-CO2 impacts of hydrogen propulsion, and we're joined by University of Leeds. So I'll do introductions in a minute. Just a few things to say up front about the webinar. Scheduled to last 1 hour. We'll be aiming for a very prompt finish at 11 a.m. As you probably saw when you joined, you may have had a notice to say this event's being recorded. So for those who couldn't attend today, we're making the recording of the presentations available after the event, and everyone will get a link to that so you can watch again. You will see in the Q&A box that you can type questions. Please do so by adding your name and organization at the front so I can introduce you when we present them to the panelists. But in a sense, don't wait until we get to the panel discussion. If you hear things as you're going through and you want to come back to them, by all means, type your question then, and we'll save them for the end of the presentation. So, quick overview of today's agenda. I'm going to say some very quick words of introduction on behalf of AEF. I'm then going to hand over to Professor Piers Forster, who will provide us with today's presentation. And then we will go to Q&A, and Piers will be joined by his colleague, Dr. Alex Rapp. And we'll go through your questions, and then very quick closing remarks from us and a few next steps. I should say that there is a summary report of today's presentation that is available on our website, and there'll be a link to that in the chat, but I'll also come back to it at the end in closing remarks. So I'm just going to say something very briefly by way of context. AEF over the last couple of years has been in a collaboration with the World Economic Forum and the Aviation Impactor Accelerator team at the University of Cambridge and McKinsey & Co, looking at the technology, infrastructure and policy requirements for electric and hydrogen aircraft propulsion. And the project was called Target True Zero, and that reflected the fact that we wanted to be sure all the partners were very united in the goal of actually not just focusing on CO2 emissions, but focusing on the total climate impact. And so, we wanted to apply that to electric and hydrogen. And really early on in the process, the AIA team at Cambridge, theirs was the first of the three reports to come out, provided us with an overview of the sort of likely non-CO2 impacts that could apply. And I think that sort of whetted the appetite, and we're very keen. If you think what's going on at the moment in the UK around the sort of Jet Zero Council and the zero emission aircraft subgroup, but also in terms of the non-CO2 task and finish group, both of those things, have a lot to learn from that initial work, and so we're keen to keep the conversation going. And so we thought it would be a good idea to invite Piers and his team at University of Leeds to think more about this topic and try and build on that work, and more importantly, what needs to happen next, and what is it that we still don't know that we need to know. And so I'm really pleased to hand over to you, Piers, for today's presentation. I'm going to stop sharing my screen, so I'd invite you to open up your screen and to do the same. While you're doing that, I will introduce you if you actually need any introduction, but I think most of you will know Piers. He's Professor of Physical Climate Change at the University of Leeds. He also holds the position of Director of the Priestley International Centre for Climate. And Piers is a renowned expert in aviation's non-CO2 impacts. He's lead author of IPCC assessments and special reports. And although he's not speaking in any way in his CCC capacity today, he is, of course, a member and interim chair of the UK Climate Change Committee. So, Piers, over to you for the presentation. Thank you.
Yeah, okay, that was a brilliant introduction, Tim. Thank you so much for that, and good morning, everyone. Yeah, I guess I put up this picture where I work in my kind of completely centre work, and I put this up because we always have to advertise where we come from. But yeah, I wanted to just tell everyone that I'm just speaking today in my university capacity as well. And to just follow on from Tim's introduction, I do think we were really excited to do this work. I'll go on one slide. I think we were really excited to do this work because we really wanted to begin to look in more detail at the possible kind of aviation industry solutions. And I think we were particularly excited to work with the Aviation Impact Accelerator team at the University of Cambridge. They're sort of competing colleagues in some kind of way, and I had been to their website and things like that, but I hadn't really had the opportunity to sit down and discuss with them the way their tool actually can work, and sort of get into some of the details behind that. So I thought it was a good opportunity to understand that the Aviation Impact Accelerator tools they are kind of producing, and to think more about the non-CO2 impacts of aviation. And this work was very much done with my kind of colleagues Alex Rapp and Debbie. Yeah, so I'll go on now. It's this the diagram you've probably all seen 100 times, depending where you come from. But this does quantify our best estimates of the impact of aviation currently. And this does it in terms of this indicator called the effective radiative pulsing, and this is the way we typically assess the effect of aviation. And this is also generally the way we assess the impact of everything within the IPCC. But I think we particularly look at the indicator with aviation, just because the aviation impact on climate change, that hasn't been very big to date. So in fact, it's quite difficult when we calculate the temperature change. It's not a very big temperature change, so it becomes quite difficult to observe it. So that's why we tend to stick to these data forcing estimates, which we can calculate a bit more accurately. But you can tell from the diagram that particularly with the non-CO2 contributions, there's still significant uncertainties. And the one we talk about, of course, is the one to do with contrails. That is by far the most significant non-CO2 contribution, but it is also worth, I think, introducing the other ones. We have the influence of nitrogen oxides, and these have quite a complex competing effect. And so if you want to look at the overall effect of nitrogen oxides, we think they contribute a warming effect currently, but that is quite uncertain because it's from this residual between two terms. So, and then there's a small influence of stratospheric water vapor increases, and this is something that is particularly influenced by if you change to a fuel like hydrogen, but you can also look at this to see that it's not particularly significant currently. The other thing I want to talk about are the potential influence of particulates and aerosols from soot and sulfur. They have a direct effect, but they also can potentially alter clouds more generally, and this is really something that we as a community haven't really investigated yet currently. So if you put all these together, there's still a big uncertainty. I better speed up, I think. Sorry. Yeah. So I thought I'd jump straight to my conclusions, and then we can come back and look at detail. So we tried to assess the literature, and so try to look at the potential of the change in the radiative forcing that comes from switching to JA1 fuel to hydrogen. And our best estimate for contrail is there could be a significant decrease in the contrail effective radiative forcing, but there's a lot of uncertainty, and there is a small chance that forcing might go up. So we can't be sure it will decrease. Yeah, and it's pretty difficult to tell what will happen to Ox, because that depends a lot on the engine design. Just as I said before, the static water vapor forcing will go up, but it's not very big. The radiative forcing that comes from particulates will disappear, but we don't know what it is currently. But it's also worth thinking about the other effects. The first is that hydrogen does potentially influence the lifetime of methane, so it does act as an indirect greenhouse gas, and so if you have a kind of 2% leakage and it has a global warming potential of about 10, this corresponds to about would correspond to about 10% of current emission to carbon dioxide. So it is certainly a significant contribution. And then, of course, we have all the issues, which I won't go into today, to do with the lifetime components. Yeah, okay, so I just want to go through some of the technical details, and particularly around contrails and aviation-induced components. So this is the scientific reason explain where precision contrails come from. You do have basically the hot and west exhaust does cool down into the kind of background conditions, and depending on the temperature and the degree of supersaturation in the background conditions, you either get persistent contrails which are the regime in number 2 on this diagram, or you get non-persistent contrails, which are the conditions in number 1 on this diagram. So, and what happens when you change the temperature and water vapor in the exhaust? You do change the actual mixing line on the diagram, so you potentially change the amount of non-persistent and persistent contrails you do kind of produce and you can see, because your hydrogen does emit a lot of water compared to kerosene, it emits about 8 times as much. Yeah, 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 yeah. You slightly alter this Appleton criteria, and these interesting diagrams by my colleagues from Paris, IPSL, does indicate the effect of switching to hydrogen. This is so if you so if you sorry, I'm drinking water. So if you look at the green line on the diagram, these are non-persistent contrails, and if you look at the blue lines on the diagram, these are the change in persistent contrails, and you can see the difference between the solid line and the dotted lines, and these are the effect of going from kerosene to hydrogen. So what they discovered for this particular example, you produce an increase in your non-persistent contrails, but you don't get much of a significant change in your persistent contrails, but they do occur more often. So you do get a slight increase in the number of persistent contrails, but there is a competing effect which acts in the opposite direction. So and this is because you don't have the same number of particulates, and this does just show some cool work by people at DLR that did fly with a 320 aircraft with different types of staff, but of course we also expect particulates in certain numbers to go down with burning hydrogen. You can see that the subparticle numbers drop when the alternative staff were burned, but while the subparticle going down, the number of ice kind of particles in the exhaust would also go down. And if you produce a contrail that doesn't have so many ice particles, you do need to bigger ice crystals, which are optically thinner, so they don't intercept the kind of radiation and much of the other ones. Because they're bigger, the particles tend to drop out, so your contrails might not be as persistent as they were. So this nice kind of modeling work by DLR did indicate that if you reduce the ice particle concentrations, you also reduce the radiative forcing as well. And so kind of work that Alex and his team did do it. Was to really try and put the different components together for the first time, because we have the effect that we might form contrails more often just from the kind of thermodynamic criteria, but we also have the effect that when we do form contrails, the contrail can radiative properties will alter and the persistence will change just because of the kind of particulate concentrations. So what he tried to do as part of the ATI zero work was to put the component together. And what I would say about our results is that these are incredibly kind of preliminary modeling investigations of what could be possibilities. So the numbers are to be taken with a pinch of salt, and you can see on the diagram we don't have uncertainties, but the uncertainties would be potential uncertainties in the sign of the response. But we went through them and we looked at these different components, and we also looked at a possible fuel cell aircraft. And we did find from our results that there is a potential significant decrease. But so I would say that the decrease is significant, but it also, the contrail rate to forcing doesn't completely disappear. And I wanted to put that kind of 30% change into wider context. So this goes back to this cool publication by colleagues at IPSL, and this looks at the change in their contrail currents just by changing altitude. And I wanted to get from this one that if you look at just the persistent contrail diagram, you can get a much bigger change in your contrails just by changing the altitude. So I did think this tells our community that we can't be relying on these alternative fuel type technologies to completely remove the non-CO2 component. There is a case to be done for particular contrail avoidance type approaches as well. And this takes on at the end of my talk, just to talk about what can fund it for us to go and collaborate with the Aviation Impact Accelerator team. What I wanted to do with the work was to go and understand the kind of what they were trying to do to put all this information together on the potential climate impact of the different components of trying to switch to the alternative technologies. And and so we try to look at their work and we talk to them about these tools. And what I was so impressed about the way they worked is that they worked in this very collaborative way where they understood that they weren't the expert in the particular component, and they were they were they were really open into trying to bring in that bring in that side of expertise to try and take the data they provided with a kind of collaborative as possible. And the other thing I was impressed by, they put a lot of work into really trying to develop the appropriate tools for different type of situations. And this is a good example where this is a tool to look at the different resource and the kind of impact from the potential alternatives. And if you do go along and look at them, it's try to quantify the impact in terms of the GWP 100 component, and it compare the effect of kerosene to the potential effect of the technology. And if we look at the contrail column, which is the last column in the climate impact one, you can see that they try and represent the uncertainties. So if the green colors on the diagram do represent an improvement over kerosene, and the red part of the diagram will represent things getting worse. So for a lot of these ones, there's a big uncertainty. So it potentially has things could either get better or get worse. But you can definitely go down and perhaps think that you can potentially come up with technologies that are improvement, and perhaps some of these uncertainties could be, if we do more kind of science and huge opportunities, I think we can potentially really begin to constrain a lot of these uncertainties to try and make them more accurate. So I think this is a really huge potential to come and do that work. And just to put some detail behind where the estimates of their contrail change comes from, and if you look at where it comes from, you can trace back in the work to try and look at that, and it does actually go back to some quite old work that is a bit out of date currently. But what I would say that the things haven't changed an awful lot, so it's probably not too inaccurate, but I think there is opportunity to really work to try and improve some of these results. Okay, so just to conclude, I think there's a good as I said before, there's a good chance that the contrail impact will not be as big and the non-CO2 impacts will not be as big. And I think there's opportunity to do a lot more work to first understand the impact of aerosols today. I think that'd be a great thing to do. And I think on fuel cell aircraft, there is some potential there, but I'm not sure they're ever going to be at the sort of altitude where they might form a lot of contrails. So that's interesting, but I think there's a lot more work we could do. So I think with that, I think I'll hand back and we can have a good discussion.
Thank you very much, Piers. That was really interesting. I'm going to bring into the discussion Dr. Alexandru Rapp. So Alex is Associate Professor of Atmospheric Science, working alongside Piers at the Priestley Centre. So welcome to the discussion. Alex Piers, you're our panelists. I should just say to a reminder to people, if you have questions about the presentation, please put them in the Q&A, and I will put them to Piers and to Alex. And I don't know, you finished, Piers, on but discussing a little bit about the Recce model and the work of the AIA team. I know the AI team were thinking of or hoping to join the call this morning. If you have and you want to say a few words, you're more than welcome to do so. Just please identify yourself in the chat, and I can make that possible. But I'm going to start off with a asking you, Alex, firstly just to introduce yourself briefly, but maybe you want to say something about your own work as well, just by way of introduction.
Yeah, that's quite good, because I think I perhaps kind of misrepresented it, Alex. So go ahead.
No, you haven't, Piers. No, you made a very good job in summarizing what we did. So, yeah, as Piers said, it was a fairly preliminary way to try and quantify some of these effects, and there's still lots of uncertainties there. So what we did in our work, where we tried to see how liquid hydrogen combustion and hydrogen fuel cell contrails might impact climate, we used the NCAR CESM contrail scheme from Chen and Gattelman, and then we essentially changed the fuel parameters in their scheme to try and simulate liquid hydrogen combustion. And then for fuel cells, we took the theoretical framework from Klaus Gierens in 2021, where he developed a way to a similar Schmidt-Appelman criteria for fuel cells. And then, yeah, we tried and investigated both the coverage, and as Piers said, we according to our results, we've seen an increase in coverage from contrails from liquid hydrogen and fuel cells compared to kerosene. But then also it's radiative forcing and effective radiative forcing. And in there, because of the fewer particulates in the exhaust, and the change in optical properties, we see a decrease in radiative forcing despite the increased coverage. One thing I should say is that our estimates are probably an upper bound in the sense that we weren't able to include the contrail lifetime effect. So because of the fewer particulates, you'll have larger contrails, contrail particles, and therefore you might expect their lifetime to be shorter. But this is an effect we weren't able to simulate in our approach, because it was a fairly short project. So this is something, in my opinion, there's a lot of room for improvement. And I'll stop there, because otherwise I'm going to say everything about the study.
I thought it was a kind of ridiculously short kind of project. And anyway, I thought you did a great job, Alex.
Yeah, you too, Piers. Yeah, so yeah, I'll just stop there. So yeah, we should take those estimates as a first attempt, and there's still many uncertainties there. But yeah.
Thanks both. The questions are starting to roll in. Seeing as we've been talking about the science, I'm gonna start with a question relates to the atmospheric sort of composition and understanding. So, question from Keith Shine. Thank you, very interesting presentation. Could you say something about how the balance between long wave warming and short wave cooling effects of contrails differs between kerosene and hydrogen?
I think I'll pass that to Alex.
I'll unmute. Yeah, it's an interesting point. We have looked at that in our report. So we tried to simulate both effects, but we didn't see a huge change in the balance of those two. From memory, I think the effect is probably I might get this the wrong way, because the contrail particles will be larger. It's likely that the shortwave will be affected more for the same sort of mass of water vapor that's condensed. Yeah. Thanks, Keith, for the question.
Yeah, Keith, with a hard question, you my old kind of supervisor, Keith. You're asking too hard questions, mate.
No, it's a very good point, because we,
Yeah.
in the way we presented results, we looked at the net effect, but obviously that is the result of the short wave and the long wave. So I'm going to try and speculate here and say that the short wave is affected more than the long wave as a percentage of the relative change, based from what I can remember. But yeah, we should definitely look at that in more detail.
I do think we do have the numbers in the ATI document, don't we, Alex, somewhere?
Yeah.
Yes.
He can't speak for himself, but Keith thanks you anyway. This might be an equally difficult question to ask, but it's a different topic. So James Beard from European Climate Foundation, also thanks you for the great presentation, but asks, based on the work that you've done so far, can you start to see whether certain hydrogen aircraft projects that are in development have more promise perhaps for non-CO2 mitigation? I mean, can you differentiate at the moment between, say, Airbus Zero E or Zero Avia? And it obviously it requires you to have some knowledge of those projects. I don't know how easy that is to answer, but answers are indeed welcome.
Sorry, can you repeat that? Because I was just trying to have a look at the shortwave and long wave thing at the same time. So
sorry, Piers. Yes, of course. So James was asking whether we see potential coming through from the hydrogen aircraft projects that are currently in development in terms of their non-CO2 mitigation potential, I suppose.
okay, well, yeah. Well, the first thing is that the fuel cell type aircraft, it does seem like they're, well, at least the first ones will be relatively short range aircraft. So actually, I think they aren't really going to contrail, so they're going to have quite a different non-CO2 component, and that does also mean that they won't be flying into the stratosphere, or I mean, they're not going to put so much water vapor up there as well. So yeah, I think their kind of non-CO2 component will be dramatically reduced compared to kind of jet we have today. But of course, you have to compare kind of like with like in some kind of way, don't you? But I think what I would say that these actual development of aircraft is really important, because we don't really understand what will be the change in the concentration of things, but just because the relationship between the aromatic component, that's not perfectly understood. We don't understand precisely the efficiency of the engines, and we don't understand what the kind of altitude that they might be at, and what are the possibility to design aircraft to fly at different altitudes and things. So, and whether they go fast or whether they go slow. So I do think the more we can put the actual engine technology, and we can work in collaboration with the people that are actually developing the new designs. I think that the more we can put realistic things into our simulations, and just because there's more change in the efficiency or a small change in the altitude can really make a very significant impact in some of the non-CO2 calculations. Yeah,
right. Yeah, I agree. And if I can add something on that, while my understanding of this concept is relatively limited at the moment, one thing we did explore in our project was the NOx effect as well. So, and from our simulations, we've seen a fairly linear response in radiative forcing due to NOx emissions. So a reduction in NOx will lead to a reduction in its climate impact in a fairly linear way. So yeah, that's one thing we should take into consideration as well, because according to the engineers involved in the FlyZero project, they were estimating a possibility of reducing NOx emissions in the case of liquid hydrogen combustion of somewhere between 30% and 60% reduction. So depending on how much you can reduce those NOx emissions, the overall non-CO2 impacts will be relatively important compared to all the other terms.
Okay, we've spoken a little bit about contrails. We've also spoken a bit about NOx just now. I'm going to move you both on to particulates. So Jayant from the International Council for Clean Transportation asks, would the reduction in particulates have the same impact as we see in low soot combustion engines, where if the soot emissions are reduced enough, the warming impact starts increasing again because of particulates entering from the atmosphere?
Perhaps I can kind of begin, and absolutely, yeah. So this goes back to the modeling work of Bernd Karker and DLR, and this is an effect that we do see in his kind of modeling work. But I think we still need to do a lot more work on that to really see if it does hold up in the kind of field world in a certain way. So we have Professor Ben Howie at the university here, and he's sort of doing this sophisticated laboratory work to try and understand which of the background pollutants do make good ice nuclei. So it will really probably depend on things like what sort of particulates are in the kind of background, and sort of precisely what part of the compelled you're in, and these sort of things. So it is probably, there's still work to be done, but we're talking about exactly the same sort of mechanism as reduced soot particles for kerosene. But the other component to that is that we don't know the relationship between the aromatic content and the amount of soot that could come out as well that well. So there is the potential that even if you got rid of the aromatic content completely, you could still be producing soot particles from the engine, from other things that are going on within the engine. So that is kind of way beyond my expertise, but perhaps someone can come and rescue me now.
Not sure about rescue, but I could also add. So yeah, the mechanism is pretty much the same. I agree. The reduction in particulates will lead to a change in contrail properties due to contrailized particles being larger, essentially. One thing I wanted to add is that while you probably expect very few, if any, particulates in the hydrogen combustion engine exhaust, work from Ben Murray that Piers has just mentioned, together with colleagues from Imperial, Mark Stettler and his group, they have seen that the lubrication oil used by the engine will also possibly generate some aerosols, and doing some studies in the lab, they have seen that those aerosols might potentially act as ice nuclei fairly efficiently. So there's still many uncertainties there, but they have published earlier this year a paper in ACP on that, on the lab experiment. So it could be that once you remove all the normal aerosol emissions from the fuel combustion, other aerosol particles might become important, and things like, as I said, lubrication oil. And obviously, in many places in the atmosphere, you've got enough aerosols in the background atmosphere to act as nuclei anyway. So you always have those background aerosols present. But yeah, in addition to that, there's possibly lubrication oil that might become relevant.
Okay, so we've considered some of the science implications. I suppose from AF's point of view, and a lot of the work that government's thinking around non-CO2 at the moment obviously has that policy dimension to it. And so I suppose, you know, I get the message. There's still lots of uncertainty, but what do you think the takeaways are for policymakers? Do you have thoughts on that, Piers or Alex?
Perhaps Alex wants to go first for change. Go on, Alex. You give your views and I give mine.
Yes, I can, but then hopefully you'll come and save me on this one. So yeah, I think that the first implication is that we still need to refine in terms of scientific answers to the question. We still need to refine a lot of work here. And then I think the other important thing to get across is that the metric that you consider is probably crucial. So while contrails have a huge effective radiative forcing, their other climate metric impact is comparatively smaller with respect to CO2. So you always have to bear in mind that for fuel cells and liquid hydrogen, you do have a lot of benefit from CO2, the CO2 term there. And then the other thing is, in addition to trying to balance their climate impact, we also need to discuss with engineers, because in the way they design the engine and the way they can make them more efficient at certain altitudes, this will also have a very important effect. So yeah, collaborating with engineers in the early stages while developing these technologies is important.
Yeah, okay, that's good. That's good. Yeah, but yeah, okay. I will start with the beginning. I think that's what the first thing to understand. I think that there is no one panacea, so there is no one kind of perfect kind of solution. So with hydrogen, of course, apart from it taking a potentially long time to develop, because we have to have a lot of kind of renewable energy and green hydrogen production, we have to get it to an aircraft, airplanes, and design the planes and all that. Despite that timing, it is still going to have a non-CO2 component to it, and potentially with its global warming potential, it will also be contributing to a greenhouse gas in some way if we can't keep it in its infrastructure. So it's not necessarily perfect, but it does have advantages over some of the other alternative aviation alternative fuels in some way, that you can potentially produce it without needing carbon dioxide removal, and the whole capacity for that might be kind of finite, and it is. So it does provide a potential long-term solution in some way that some other technologies don't do. But if you look at a potential solution like contrail avoidance, that's also not a panacea, of course, because you might produce more carbon dioxide. But in the course, then you get on to talking about limiting demand and things in the kind of shorter term. So So I think ultimately you do probably have to put all these things together in some way. You have to try and reduce the carbon dioxide footprint. You have to also do particular kind of targeted things to reduce your non-CO2 components, and that could be through engine design, changing altitudes and these sort of things. Um, uh, uh, um, 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 and you have to look at the demand side components as well, probably, or putting up cost of it in some way. So yeah, so there's not going to be one perfect solution, but that doesn't also tell that these solutions don't have a lot of worth. So I'm quite excited about the possibility of the whole industry being kind of transformed in some kind of way.
Yeah, it's good to sort of begin to wrap up the Q&A with talking about the potential, and as you say, that optimism. And I mean, to put some numbers on it, I think if you look at the government's Jet Zero strategy in the UK, I mean, I think combining hydrogen and electric together, you only get about 4% of the emission reduction in 2050. But more importantly, it represents something like 27% of the movements. So it does seem to suggest that, or the forecast seems to suggest that we see quite large scale markets developing by 2050, albeit on sort of shorter networks and routes. And I think part of today's discussion has really had that in mind, like, you know, is that potential and that optimism sort of well placed, and obviously answering the CO2 questions is one way of doing that. We've sort of more or less come to time. So I'm going to let you off further questions. I'm going to say thank you to both of you for your contributions, both the work that led to today's presentation, the presentation, and the Q&A answers. I'm just going to say a few words in terms of wrap up. So if I go back to my presentation, a few things just to say before I go on to closing remarks. Firstly, as I said at the outset, there is a summary report that accompanies the presentation today. You can download that from our website. We'll send you the link afterwards if you can't note that, and there should be a link in the chat as well. Secondly, you will all receive a recording of today's presentation. Sometimes takes a day or so to put that together and edit it. So I'm not promising a day, but you should get it either by the end of this week or early next week. So in terms of our take on this, I think we were obviously very pleased to receive your comments, Piers and Alex. I think, you know, you sort of ended on a note of optimism, and I think it's something that we share as well, or at least see as good news. I think the most fundamental question that needed answering was, you know, do hydrogen propelled aircraft have the ability to be better than kerosene? And obviously you score that highly in terms of CO2, but there was this non-CO2 question, and it sounds like from the preliminary work that you've done that they're certainly no worse, and there is a potential benefit there. And I think that's good to hear. And I think whilst there are still really big challenges remaining to bringing sort of hydrogen aircraft to market, and certainly in the scale that Jet Zero envisages by 2050, the fact that this potential exists to reduce the total climatic impact compared to conventional aircraft suggests that it's certainly well worth continuing with the R&D in this field and answering those research questions that you've posed to us in your presentation. The next steps, the things that need to be done, certainly seems worthwhile taking those steps. I think at the end of the day, we have to be really mindful that this technology, if we just look at CO2, isn't going to be climate neutral. And even if you meet the sort of preconditions for making green hydrogen at scale, you know, this is still a really important area. The non-CO2 impacts, this is a really important area for us to focus on, and for policymakers as well. You know, we started to dabble at the end into the discussions about sort of contrail avoidance and those big policy questions, and maybe what we can't solve through the technology, you know, that's a very much a live discussion in terms of, do these mitigation measures that we're currently considering for conventionally fueled aircraft equally apply to hydrogen as well? So obviously we have to do all of that in parallel. So I'm going to wrap the call up and say a big thank you to Alex and Piers for your comments today, and for your colleague, Dr. Debbie Rosen, who didn't join us today, but was very sort of instrumental in helping with the report as well. Thanks everyone for joining. My last comment is to say, I mentioned right at the beginning that this is the second in a series of 3 webinars we're holding in January. So we had Tyndall Centre on Ammonia last week, Piers and Alex today from University of Leeds talking about non-CO2 impacts of hydrogen. We finished the series next Wednesday with a presentation from Chris Mallins from the consultancy Serology. Chris is an leading expert in alternative fuels, and he's talking to us about some of the issues currently facing SAF, everything from the sort of life cycle assessment methodologies and approaches through to the use of waste. So you will receive an invite to join us next Wednesday for the 3rd and final seminar. So thank you to everyone, and say thank you to our presenters, and I look forward to seeing most of you next week. Thanks very much.